today we're going to start applications to derivatives. To me, this is a fun chapter. It's where it starts making sense why we would do all of this derivative stuff. If you are a science person, this is where you will really start to enjoy calculus. At this point, we've just done a bunch of formula chasing, figuring out how to find derivatives and looking at graphs of derivatives. But now we're going to start to look at where we can use those. Today is going to be very little calculus work and a little bit more interpreting some words from word problems and how we can place those in a calculus problem. And then tomorrow we'll start connecting that to actual calculus problems. Tomorrow we will start motion, velocity, position, acceleration. Those of you physics people, you've already learned it. It'll be a little boring, but and then we'll do a topic called optimization. And then we'll do related rates. So those are the three topics for this chapter. It is one of my favorite chapters. It is word problems, so you probably all won't share my enthusiasm, but some of you. Okay, so for what value, this has nothing to do with application, just an AP practice problem, of k will x plus k over x have a relative maximum at x equals -2. So that's some function f of x. If it has a relative maximum at x equals -2, what could we do? Where? Just here. Into the derivative. Why? Set it equal to 0. Why would we set it equal to 0 in the derivative? Because it's a critical value. So, the derivative of x is 1. I highly recommend a rewrite on this. You don't have to, but wouldn't you rather do the derivative of that than k over x with quotient rule? So the derivative is 1 minus kx to the -2. I'm going to plug -2 in for x. Am I going too fast? And so that equals to 0. -2 raised to -2 power is 1/4. So we're going to look at how I do that. Negative flips and square. So 1 minus k over 4 equals 0. So k is 4. Any questions about that? That's probably the answer. So today we're going to be looking at how we can apply real-world problems to calculus, or calculus to real-world problems. We've talked about it, hinted around at it, but haven't actually got there. So first let's talk about what f of x tells us, what the first derivative tells us, and what the second derivative tells us. The original function is typically a quantity. Now, of course, we could have it be the original function be a velocity, but typically we have the original function be a quantity, a position, an amount of things, something like that. If we are doing position, it would be in feet. And if we're doing quantity, it would be something like gallons or something like that. The first derivative, as you know, is the instantaneous rate of change, or the rate of change of that quantity. If you're doing gallons, maybe it's gallons per hour. In this example up here, it's feet per second, the velocity. Let's talk a little bit about why that would be. What is slope from Algebra 1? Rise over run, or change in y over change in x. So if your y is measured in feet and your x is measured in seconds, you see how you would get feet over seconds, feet per second if you do the slope. So that makes sense units-wise as well. The second derivative is the rate of change of the rate of change. that could be gallons per hour, or feet per second, or feet per second squared. That is an acceleration, the rate of change of the velocity. So in real-world situations, a rate or a speed is a derivative, and a correct understanding of units is very, very important. Do you see why the slope of the slope would give you feet per second squared? Because change in y would be in feet per second over seconds. So you would get feet per second or feet per second squared. Today is definitely going to feel a little strange as far as calculus goes. It's not something we'll spend a lot of time doing just one day on it, but we're just going to look at some real-world situations and identify the function. We're going to identify the derivative, identify the second derivative, and sketch a graph of what that might look like. This is just a cartoon, but it's example number 1. So this is a Garfield cartoon. And Garfield is saying, I'm proud to report that I've gained only 1 pound. With Garfield, the goal of the diet isn't losing weight, it's slowing down the gain. So from this situation, let's talk about what would f of x be, what would f prime be, and what would f double prime be. What is f of x in this situation? What's the quantity that we have here? His weight. His weight. Questions about how we would pick that quantity out? There's not really a problem here, right? It's just picking out f prime, f double prime. Is Garfield's weight positive, 0, or negative? Positive. Not because he's gaining. It's just he weighs something, right? What is f prime in this situation? The rate of change of his weight, right? The rate of change of Garfield's weight. Is that positive, negative, or 0? He is gaining weight, right? So he is increasing his weight.
All of our problems be like this one.
Probably not.
Maybe like one every homework or something.
With a card. Yep. What about f double prime? Rate of change of the rate of change.
ROC.
Yeah, you could write like rate of change of that. future, the short way to write that is F double prime. Explaining what it means, the short way. And you won't write this forever, I promise. Is that positive, negative, or zero? Why is it negative?
The goal is to slow down the gain.
Slow down the weight gain. So he is decreasing the rate of change of his weight gain. Does that make sense? Okay, so that's an example. Try this one. This one's tough. I'm giving you time so you can write the problem if you want.
Answer it for me.
Okay, what's the quantity you see here? Good. HIV infections. Now, how you define F of X does affect your other answer, right? But I think that's a good pick. The number of HIV cases, right? Quantity. Is that positive, negative, or zero? Positive.
So it's positive because there is an infection.
Right.
No matter, like, so, no matter if it's like up and down, the person thinks that there is.
Right.
No matter.
For the most part, now, depending on the function, if we're talking about a position, you could have left of center or right of center. So you might call position negative because of the location. But yeah, I mean, a lot of quantities are going to be positive. So a lot of things we're going to start with a positive value. What is F prime? Rate of change of HIV cases. The rate of new HIV infections in sub-Saharan Africa has slowly declined. Okay, what do you think?
It's declining, but it's still there.
I feel like it's like one of those.
I think it's
We think it's positive. Why? Are we getting new HIV cases? So are we adding to the HIV total?
even though it's lower, it's still lower.
Right. We are adding, even though less, we are adding HIV cases. Rate of change of the rate of change. this is talking about, right? The rate of new infections, right? It's declining. Now, I do want to talk about a way that your answer could be correct in different times. If you said that f of x was the new HIV cases, would that change the problem? And so some people who work this problem label f of x differently and call it new HIV cases. In which case, the new infections is lower in 2008. Does everyone see that? So if you had labeled your f of x as new HIV cases, then f prime would actually be negative because there are less new cases. Does everyone see that?
So it'd be positive, negative, negative.
It would be positive, negative, negative. So it does depend on what you name x or f of x, right? Is that going to be the case with anything? Yeah. So it does depend on how you label. What does this look like? Probably starts up here somewhere, right? Any questions about that? Yeah. You see how it's slowing the increase? John, you would have been completely correct if you had labeled this two HIV cases and then you had positive, negative, negative. Part of it depends on your definition of FMX.
Wouldn't it have been easier like that since it says like declining in the first
Probably.
place?
In the third hour, I may do it that way. Listen to what y'all tell me to do. But both are correct. Both are correct options. Consider the following examples to think about what slope of the derivative might have to do with the situation. It is estimated that for T years from now, the circulation of a newspaper can be modeled by this formula. At what rate will the circulation be changing with respect to time 5 years from now? So circulation is probably how many newspapers are in circulation. That's probably a quantity of newspapers. At what rate will the circulation be changing 5 years from now? How is a derivative important to that? Derivative is the rate of change. So would you agree that I just need to find C prime of 5? And then I would have the answer to this question. I just want to know the rate of change of the circulation. So let's find C prime of T. What do I have to do on the 15T natural log T? That's a little bit different. Left, right, plus right.
Flipping the 5 for the T. Is that what you're doing?
We will, I have not yet.
But is that what you're doing with the equation?
And finding the derivative and then I will plug in the 5 and something else. Plus right, left. You could simplify first, or you could just go ahead and plug in 5. Depending on this, if this is a calculator problem or a non-calculator problem, we could plug that into the calculator. Will someone do that for me? Why is this probably a calculator problem? Natural log 5. Right? I don't know what the natural log 5 is. Now you could leave it as a natural log 5 and does fall on a non-calculator problem.
1,530 points.
Like 472. What would my units be? Newspapers per year. So what that means is the circulation of the newspapers is changing by 1,530 newspapers per year after 5 years. Now, could that rate of change? Yeah, you know, as our population ages, newspapers are declining, right? So, yeah, that could change. Now, this actually is positive, so it appears that they are gaining newspapers. Who knows how outdated this problem is. So the rate of change is not constant. That's where calculus comes into play. Before calculus, you could only work with things that had a constant rate of change. Well, we know in a very changing world, rates of change all the time. So that's where calculus comes into play. Okay. Imagine that a large diamond is dropped into a lake. The experience suggests that the impact would create a series of concentric waves, emanting from the point at which the diamond hit the water out of the microscope. Find the rate of change of the area of a circle with respect to its radius. First of all, what is the area of a circle? Area equals pi r squared. If I call that a function of r, can I take the derivative of it? So, dA over dr would be 2 pi r. That's what it is. Math nerds, any math nerds in here? So the rate of change of the area is 2 pi r. Why is that a little strange? Evaluate the rate of change of the area at r equals 5. 10 pi. If r is measured in inches, what would the appropriate units be for the rate of change of the area over dr? Well, remember it's y over x, right? Or in this case, a over r. That's where that Newton's notation actually comes in quite handy, because you see what is the y value and what is the x value. What would the units be for the area? Change in area. Inches squared. What would the units be for the radius? Inches. So we would get inches squared per inch. Normally we just leave it that way. What is inches squared over inches? That makes sense for circumference, doesn't it? What are units for area? Like if you're finding the area of 4, what are units?
I have no idea.
Square inches. Like the kind of units you would get on area would be square units, and since we're inches, it would be square inches.
So instead of there, it's in inches.
Well, actually, that's kind of, but if r is measured in inches, wouldn't area also be in inches, but it's just square distance, because it's area instead of just a distance. So you put the units of A over the units of R. You can. Normally they're going to be like feet per second, so you can really simplify. But if they happen to be simplified, go for it. today, the whole point of today is to just practice getting familiar with picking out from a word problem what's what. Things we're not actually doing a whole lot of math today, although there are a couple of little problems on the homework. But mainly today, getting familiar with how a word problem relates to other problems. You have your homework. You have 20 minutes left in class. No, we're on a 15 minutes left in class. So fucking words, questions. It's not that much work though if you look at it like numbers 1 and 2.